The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees. ACI web sessions are recorded at ACI conventions or other concrete industry events and will be made available for viewing free of charge for 1 week. Thereafter, they will be archived on the ACI website or added to ACI's online CEU program, depending on their content.
Our next speaker is Professor Jason Weiss. Professor Jason Weiss is a professor of civil engineering at Purdue University. He's well known for his contribution in the area of mass transport in concrete, electrical properties, internal curing, and deterioration mechanics.
Okay, well, thank you very much. And we've had 5 fantastic talks. Let's hope we don't wreck the car in the last lap here of the session. But what I really want to do is talk a little bit about some of the resistivity work that we're doing. And I really want to focus in on just the test method itself and really where we're talking about mixture acceptance and some of the factors that could influence this. Really, I think what we're after here is, much like Indiana Jones, we're on the quest for the Holy Grail. We want a test that tells us something about transport, whether it's diffusion, whether it's permeability, whether it's absorption, whatever that particular mechanism is. We want it fast, we want it accurate, we want it inexpensive. But I think in addition to those things, we'd like something that's also scientifically valid, right? We've seen and we've heard a lot of different speakers as we've gone through that there are other things that can influence the electrical results. And if we're not careful, we can be measuring some of these other effects and not really be aware of it. So I think it's very important that as I go through and I'll point out several of the caveats, I think this is an excellent test for the first 4 or 5 reasons here that we've seen, but I think we have to be careful when we're running some of these tests to make sure that we're still making sure that we're measuring what we're trying to measure in the overall system. All right. The main thing I want to try to start off with, and I want to really try to remind us on, is really most of the transport that we're talking about is happening in the capillary pores. All right. And to coin a separate term, we may say that this is happening in the BFPs, the big fat pores. The majority of the transport is going to happen in the capillary pores, which are going to be the bigger pores. They're going to be the connected pores. They're going to be the pores that we control with water to cement ratio. So when we start to think about transport, we really have to think about our friends the sopranos. All right, transport is really dictated by the pores that are big and the pores that are connected. All right, so really we're trying to get a measure that tells us about the pore volume and its connectedness, and this is why electrical properties are really what we're after. So it's really the paste portion that we're interested in, and we can describe the volume of these big pores, right? They change with hydration, they change with water to cement ratio. So it's really porosity changing with time, temperature, and moisture content that's really what we're trying to look at. And if we just looked at this from a resistivity type of approach, we can see here that the imaginary versus the real impedance, as we change the water to cement ratio, as we go to a lower water to cement ratio, we typically change the volume of pore fluid in the system. So resistance is a way that we can pick up on that. And if we change the degree of hydration, again, we change the volume of the pores in the system so we can pick up on this. And there's nothing shocking by this. When we change the volume of the pores, we change the resistance. But what I want to really draw attention to here very quickly is I want to draw attention to the fact that geometry is very important. And if I ask people in here, is stiffness a material property, we'd probably get a variety of different hands going up. Stiffness may or may not be a material property. But if we look at this, load versus deformation isn't the same if we have 2 different size samples. Right? We have 2 different geometries. Stiffness is not a material property. It depends on the geometry of the sample that you're looking at. If we convert this over to stress and strain, we can get our elastic modulus, which is a material property, which is independent of the geometry that we're looking at. Resistance is very similar to this. And if we look at tests with different geometries or samples with different geometries or different end conditions, we will get a very different resistance. But if we correct those for the geometry, we get a single value of resistivity that should be the same between every single test. And what we've tried to look at is we've said there are really 3 classes of tests that are out there that people are using. There's the surface resistivity test that we've seen. There's the uniaxial test, which we've seen talked about as well. And there's tests where you could actually just drop embedded electrodes into the sample. And if all of these are measuring a material property, all three of these results should correspond to each other and give you the same number. Now, one of the things that's important is when you're using the surface resistivity, there's a correction that applies to the spacing of the probes, but there's also a correction that applies to the cylindrical geometry that has to be applied. So this can be done down here. Uniaxial is easy because we're just correcting for area. And then any other geometry that we would use, there are ways to calculate what that particular geometry factor is. And if you do that, one of the things that you will notice is, irrespective of the equipment that's being used, typically for most of the commercial manufacturers, all right, and irrespective of the geometry, you get a very similar value once the correct geometric correction is performed. The one thing I do want to point out is it's very, very important that we have a reference material that we can measure this resistivity off of, because you can see some values that are down here. These particular values were one of the particular manufacturers with a low battery in the equipment. Gives you a measurement, but if you're not checking against a specific resistor, so you know what the resistance is for that calibrated piece of equipment, all right, you're going to measure a number that's not anywhere near what it should have been, all right, for the right system. Now, the other thing that I want to start off with, and I want to sort of push through on this, and I want to try to drive this home, a lot of what we're going to talk about is based on Archie's law. Not this Archie, a slightly different Archie. But the basic idea here is we're going to talk about the resistivity, and as we've heard a couple times, it's going to be related to the pores, it's going to be related to the connectedness, and it's going to be related to the pore solution property. So this equation down here that we're going to talk about is saying that the resistivity is related to whatever the fluids are that are inside of the system and how conductive that is, and phi beta. Now this phi beta we can think about as the fluid-filled porosity and the connectedness of that fluid, but if we define this in a saturated system, that describes the microstructure of our system. So anything that's not looking at that in a saturated system, we are going to have to correct this to account for moisture. We're going to have to correct this to account for leaching. We're going to have to correct this to account for other things that might be happening in the system. We also assume when we start to apply this type of approach that everything else in the system is not conductive. Right? There are ways that you can count for conductive aggregates inside of the system, whether it's a conductive aggregate based on the original source or whether it's a porous aggregate that happens to be conductive. There are ways to account for that, and this equation just is slightly modified, and depending upon the mix, it may or may not be important. But for the majority of concrete, we can describe this way, where we can say the conductivity or the resistivity of our total concrete is the resistivity of the pore solution times this factor that describes both the volume of the pores and the connectedness of the pores. And as we go back to our Sopranos, remember that it's the volume, big pores, and it's the connectedness of the pores that are really important. Now, there are ways to get this pore solution, and there are really three ways. This is really sort of a painful process for most real concretes. We could extract the pore solution, or we could squeeze it like an orange, get the juice out of it, measure the resistivity of that pore solution. It is a painful process for good concretes. Very easy to do at early ages. There are embedded sensors that you could drop in, and you could measure the resistivity as a function of time and how that changes. Or you could do a simple calculation, all right, based on some theoretical concepts. One of the things that I want to point out as we go through this, and all three of those methods are really valid, one thing that's very, very important is these predictive methods work really well after you've passed that sulfate depletion peak in the hydration curve. So once you're out in this region, and this green line is what you would predict from that website that I just mentioned where they assume some alkalis are bound, right? You can see here that the experimental data sort of drops off after the sulfate depletion peak, and I apologize, this should show the heat curve and should show you that the conductivity or resistivity changes right after the sulfate depletion peak, and anybody who wants to see the actual evidence of that, I'll send you the full set of data. But what's also important is this pore solution conductivity is relatively linearly proportional to the degree of hydration. And if you stop and think about it, the reason it's proportional to the degree of hydration is because the volume of the porosity is proportional to the degree of hydration. The pore solution is becoming more concentrated. So at a first order, it's relatively linear proportional after about the first 24 hours when you get past that sulfate depletion peak. Now, one of the reasons that we got into this is because this is a very fast test method that can be used, and what we wanted to try to do was we wanted to try to quantify some of the variability. So we went through and we started to look at what's the machine variability, which is really, really low in most of these cases, operator, the materials, the production. One of the things that's kind of interesting is if you look at this and you look at only a single lab where you're looking at the variability, you've got a coefficient of variation of 2 or 3%. You're down at a very low variability range. However, when you start looking at production variability, you start taking this out to the field, you see that value start to grow. So here is some data from a paving project where they ran this throughout the course of the summer, same mix essentially all summer long, coefficient of variation of around 10%. And essentially, one of the things that we really started to look at is, well, is all of that production variability when we start to look at this? Now, we did a round-robin study where we had 12 different groups, 12 different states, and one of the things we noticed is the within-lab variation was about 4% coefficient of variation. However, when we started to look at multi-labs, right, we noticed that this jumped up substantially. And so there were sample exchanges. And one of the things that we saw was, in addition to the machine and operator error, there really seems to be a big component of this that's based on how the samples are handled, conditioned, and cured. Now, if we asked anybody before we started, is handling the samples very important? Is talking about the samples very important? Yes, it's vital, but these are all following the standard. All right, so everyone was following the AASHTO provisional standard here, curing the samples, all right, and the variation was very, very high in the system. To follow up on this, what we did was we prepared samples and distributed them to 10 different labs throughout the state of Indiana. And here you can see these. These were distributed after 2.5 days. Took them to different people, had them do their measurements, store them in their labs under standard conditions. These are the same samples, right, where we measured them up to 90 days and then took them and distributed to the same test labs and had them measure them after that period of time. And what you will notice here, this variability is much higher than when we took them, the mature samples that had all been conditioned together. This implies that the conditioning is incredibly important in these samples, and paying attention to the moisture, paying attention to the temperature, paying attention to the humidity is very, very important because that has a big impact on the results of this test. So one of the things that we started to try to do was to quantify several of these different effects that we've heard people talking about this morning. So we said that this first part of this equation is exactly what we've been talking about: pore solution, the formation factor, which describes the saturated system, describes essentially the microstructure of the system. But then we're going to talk about the moisture content, the testing temperature, and the leaching. The one thing I will mention is we've also looked at equivalent ages, and we've looked at accelerated aging. I'm not going to talk about any of that today. I'm just going to talk about the role of saturation, temperature at testing, and leaching as we start to go through this process. Right, so as was mentioned a little bit earlier, saturation is a very big important component of this, and the saturation level does really two things. It decreases the volume of the conductive fluid, it makes that fluid more concentrated, and it also changes the connectivity of that fluid dramatically. So one of the things that you will see here is the saturation function that we're going to use is saturation raised to some power, and that power is a value of about 4. So if you have a saturation of about 90% in the system, your results are going to be 65% different by the time you start to raise this. Right now, I want to mention here, this is not relative humidity because relative humidity is highly nonlinear with degree of saturation at very high levels. All right, so if you looked at this, here's the actual data to show you this particular test was around 3.4. This is the conductivity measured from a completely separate set of experiments where we were looking at drying. And here you can notice that this is a log scale. We see an enormous change in the conductivity or the resistivity that can be completely described by this model up until you get to a point of about 50 or 60% relative humidity. And the reason that it stops to work really well at 50 or 60% relative humidity is mainly because the pores dry out at that point, the capillary pores are almost empty, and almost all the conduction is happening through the gel pores in the overall system. Right, in addition to this, we took the same samples, we stored them in 2 different solutions. So here you can see a lime-saturated solution, a pore solution, and if you change the temperature of the samples, we can describe the change in temperature using just an Arrhenius type of approach like you see here. What's interesting about this is the activation energy changes depending upon the storage solution. And you may say, well, that sounds completely insane, and that's why we started to look into this. Why would the activation energy change if you just took pore solutions and changed the temperature versus a bulk sample and changed the temperature of this? And the reason for this is because what's being captured in this particular test is not only the effect of temperature, but it's the effect of leaching, like Mike mentioned earlier. So even at very short times placing these samples into a bucket of water, there can be substantial leaching taking place inside of these samples. Right? Remember, the volume of the pores to the volume of the fluid is enormous when you put a cylinder into a bucket. And it makes a big difference whether you put a cylinder into a bucket or 10 cylinders into a bucket or a cylinder into a trough because of the amount of leaching that can take place in the system. So as was talked about earlier, if you get leaching in the system, you dramatically change the overall system. Now, as was mentioned earlier, a couple different people talked about there is a relationship between RCPT and resistivity, and we went through the literature and we found that there are about 12 different relationships that people used to describe this based on empirical evidence. And when you look at this, they all have roughly the same shape, right? Which is good because you should be able to get a resistivity test to measure the resistivity of the sample. And both of these are measuring the same thing. They're measuring the resistivity of the sample. But if you look in here, there's a huge spread, and we believe that one of the reasons that we're seeing this huge spread is the lack of accounting for degree of saturation and the lack of accounting for the leaching that can take place in the system. So what we tried to do is we took the exact same concretes here and we stored them in different conditions. So what you will see is we have a sample stored in lime water at 45 degrees, sample stored in pore solution at 45 degrees, sealed sample, then 2 samples that were sealed and vacuum saturated at the time of testing. And we're going to compare those with a steady state diffusion cell, which we see as this solid line across the bottom. Now, if we measured these and we used the same pore solution to do the correction, we would get a formation factor from all of these samples that varies quite a bit. Right? Varies pretty substantially. And it shouldn't, because these are the same samples, cast at the same time. The only difference is the way that they were cured. If we go through and use this model that's been formulated to describe temperature, to describe leaching, to describe degree of saturation, all of these results start to fall into a band. And the reason that some of the leaching is very different at higher temperatures is because the activation energy associated with leaching means higher temperatures, faster leaching, and that's faster than what you're going to see in some of those conductivity temperature corrections. We also think that this can go a long way to describing some of what people have seen anecdotally in the literature, or where there have been papers where Virginia and some of the guidance from NRMCA says if you use accelerated curing, you may get to the same equivalent age, but you may not necessarily have the same transport properties at that particular time. And we think one explanation of this is the leaching that occurs, especially when the samples are stored in water. So we think that one of the real things that we need to do is we need to account for these if we really want to hone in on the exact properties of the system. So in summary, all right, controlling water content and water to cement ratio are the first items that we really want to be able to do for field testing. Resistivity is a great method to use to get the first crack at this. Testing geometry is incredibly important and needs to be accounted for, and it needs to be accounted for properly. Variation, all right, the testing can be low, but the curing and storage seems to be a huge part of this. All right, and right now the standard says you can store it in a wet room, you can store it in a bucket, all right, you can store it some other way. We really need to tighten that up, and we really need to start to account for the leaching that can occur in those systems. Temperature, leaching, and saturation are all very, very important, and there are ways to describe this. Right? We've begun an approach where we're really looking at sealed samples because we think from a production point of view this is something that could be easily done and easily implemented. So the whole idea is you could qualify a mixture and you could go through the level of detail that you want to go through here, whether it's qualifying it based on a RCPT test, whether it's based on a diffusion test, whether it's based on something else, and you can come up with essentially a resistivity master curve where the samples are sealed and you could correct for your degree of saturation. Then while you're doing your quality control, you're essentially taking your measurements during the construction process, right? You now can get repeatability on this because what you're really trying to see is, have we gotten a different water to cement ratio or water content during production? It's easy to test this and it's easy to know, have you lost moisture from the time that the sample's been prepared, because you can simply weigh the sample at the beginning and the end, and it can give you indications on what variations have taken place during the construction process to try to bring that back to how those changes may affect the service life of the particular element you're looking at. So with that, I'll turn it back over if there are questions. Right, hopefully we didn't crash the car on the way through the final lap. So the question here is, which is it more important for? It actually happens in both samples. It becomes a much bigger factor, especially when you're doing the geometry correction for surface versus bulk, because that ratio changes. And Mike pointed this out, and then there was someone who talked about moisture penetration during the test. What we have is we have really significant changes in the layers, and that surface layer leaches much faster than the core does. So what you can actually see is the ratio between surface and bulk changes dramatically, and it gives you some results that really look funny. If you start plotting them over time, you actually get a huge change. So the surface resistivity is much more affected at very early ages, and I think it's much more sensitive to the overall system that you're looking at. But it happens in both. It's just a bigger portion of both. And you can easily model it, and it's been done. Other questions? Don't get in the way of lunch. Doug. Yeah, so just to go back on why we're leaning toward the sealed way right now is essentially, even if you put it into a bucket filled with water, it's not saturated after 90 days. You can take that sample, dry it out, resaturate in a vacuum, and you find out that you're not anywhere near saturation. So we're not at saturation when it's in a bucket, plus we're providing it all the opportunity that we can to leach like crazy. Now, if we wanted to, you could put it in a bucket with near pore solution, but for some mixtures, this becomes a tricky endeavor because which pore solution do you use? Do you use a 1-day pore solution, a 5-day pore solution, a 90-day pore solution? And I mean, all of those are better than sticking it in water, but it becomes a bigger logistical issue, we think, when you start to go to the field. We had questions on even, calcium hydroxide, how much do you put in from people who are doing this in the field? And I think trying to come up with an alkali balance is going to be trickier. So the nice thing is with the sealed sample, you just have to correct for the degree of saturation, but the degree of saturation should be something that you could easily measure if you needed to, and should stay relatively consistent through the different mixtures. And then you can also take the cylinder out if you want to break it or you want to do any other wild exotic thing to the cylinder, you've got it. Okay. Thank you.
Thank you very much.